Good evening and happy Wednesday. Already in the month of August. Hard to believe the summer's almost over already. So we finished up with derivatives last time. And we're now going to look at their applications. Tonight, we look at related rates. Right. Related rates are just problems in which variables and their rates of change are related to each other. We also look at approximations this evening. So starting with related rates, the best way to explain these is just to jump right into some problems. Okay. So here we're told that water flows onto a flat surface at a rate of 5 cubic centimeters per second, forming a circular puddle that is 10 millimeters deep. We're asked to determine how fast the radius is growing when the radius is one of 3 measures. Generally speaking, the hardest part of a related rates problem is the setup. Solving it is, generally speaking, fairly simple. So let's first just write out what we're given. What do we know? All right, so there's the first piece of information. I can actually just use a highlighter. The keyword is rate. So you know that's going to be a derivative. Cubic centimeter is a volume. So we're given the rate of change of volume with respect to time. There's the next piece of information. A circular puddle, 10 millimeters deep. It's going to create the variable d for depth. And that's 10 millimeters. And that's what we want to find. And so how fast is the radius growing? Well, that is a rate of change of radius. Specifically, when the radius is equal to some value R naught. Well, we have a problem right off the bat. Who sees what the issue is?
Is it the units of measurement?
We have two different units of measurement, right? Volume is in cubic centimeters, but the depth is in millimeters. This means that we're going to have to convert one of them. The easiest one to convert would be the depth. Right, so convert 10 millimeters into centimeters. It's just one, isn't it? Now we have to find the model. Now we have volume. We have depth. One of the formulas you should have learned from geometry. Volume is equal to a cross-sectional area times the depth or the height. Well, we're given D, right? D is 1. What about A? It's a circular puddle. So our cross sections are circles. Area of a circle. Pi r squared. We now differentiate this with respect to time. Right, pi is a constant, right? But r squared can change. So we differentiate r squared. To r dr dt. All right, got Right? Typically, what I like to do at this point is solve for what we're trying to find, right? Which in this case is drdt. But we know dv dt, right? It's 5. There's our equation. All right, there's our relation. Right, now if you want to, I'm going to write this as a function. Right, so remember the dot notation? Let's also write out what it's going to be measured in. So what are the units?
Centimeters cubed per second.
Centimeters cubed per second? Okay. So come back to here, right? drdt. What is r? And so what is r measuring in? What are the units?
Measuring the radius in centimeters.
So it shouldn't be cubic centimeters, right? It should just be centimeters per second. Right, so whenever you're looking at rates of change, the units, right, just look at, essentially, calling it the numerator, right? dr, so centimeters, dt, seconds, centimeters per second. Right, so we wanted what? We wanted 1 centimeter. Radius is growing at a rate of 5 over 2 pi centimeters per second. Part B was 10 centimeters. One over 4 pi centimeters per second. You may also see that written this way. And we also wanted 100 centimeters. Right, 1 over 40 pi centimeters per second. Right, so first thing you want to do is first just read the problem. Then go back and reread it and write down the information that you're given, as well as what you want to find. Then usually the toughest part, you need a model. And so you need a relation for your knowns and unknowns. Differentiate it. And then solve for the unknown that you want to find. That's too similar. So I'll just do this one. F-22 aircraft flying 500 miles per hour with an elevation of 10,000 feet on a straight line path that will take it directly over an anti-aircraft gun. How fast must the gun be able to turn to accurately track the aircraft when the plane is a mile away, a fifth of a mile away, and then directly overhead? Whenever you can, draw a picture. And then label stuff on this picture. As you can see, this problem breaks down to a right triangle. Right, so here what we're doing is we're letting x represent the distance, the vertical distance, no, the horizontal distance the plane is away from the gun. We're assuming that it's flying at a constant 10,000 foot elevation. And we know it's flying towards at 500 miles per hour. Right. Now let's just write down what we know. We know dx dt. It's negative 500 miles per hour. Right. Negative because the distance x is decreasing, right? It's shrinking. Y the elevation, or yeah, y the elevation we know is 10,000 feet. We want to determine d theta dt. So we want to determine how the angle's changing when the plane is some distance away. Well, again, you should notice that we don't have the same units. So let's convert miles per hour into foot per hour. What is it, 5280 feet in a mile? Yes. There's 5,280 feet in 1 mile. Right, so we have to multiply the negative 500 by 5280. We could use scientific notation. Nah, doesn't really matter. Just however you want to do it. So we want a relation between theta, x, and y. Oops, did that backwards. It's x over 10 to the fourth. Cotangent. Adjacent over opposite, right? Now we need to differentiate. So derivative of cotangent. Negative cosecant squared. Right, and then don't forget theta is changing, so we have to multiply by d theta dt. The right-hand side would just be dx dt over 10 to the fourth. We know what the dx dt is. We get 264 times sine squared of theta. Evaluating this, when x is some value x naught, we're going to get 264 times sine squared of theta evaluated at x equals x naught. Okay. What is sine squared of theta when x is equal to x naught? Well, come back up to the triangle. Sine of theta is what? Opposite over hypotenuse, right? The opposite's 10 to the fourth. But what's the hypotenuse? Well, we look at our good friend Pythagoras for that, don't we? Sum of the square of the sides is equal to the square of the hypotenuse. The x squared, square root of x squared plus 10,000 squared, which is just 10 to the 8th. And that whole thing gets squared. So what we wind up with is 264 times 10 to the 8th over x naught squared plus 10 to the 8th. Right, or 2.64 times 10 to the 10th over x naught squared plus 10 to the 8th. And then you look at, okay, what are the units going to be? Well, it's units for theta. Which is the radian, right? Per units of time, which is second. So this is what we're going to be using. So first up, we wanted 1 mile, right? We wanted 1 mile away, so x naught is a mile. We need that in feet. All right, so 5280 feet. Oh, I'm sorry. Time is not in seconds, is it? Time is in hours. Okay, oh boy. So let's look at this. We have 2.64 times 10 to the 10th divided by 5280 squared plus 10 to the 8th. Wow, poopers. It is giving it to me as a decimal, which I don't want, which means I have to write this out the hard way. So here's what we get in exact form. And it looks hideous. Right, just for perspective, this is about 206.45. All right, we wanted next 1/5 of a mile. Well, that's 5280 divided by 5. Right, which is 1,056 feet. All right, just plug in 1056 in for X naught. Oh my, this one looks even worse. And again, just for some context, it's about 261.09. All right. And finally, we wanted it when it was directly overhead. Well, that would make our distance, X naught, what? It would be 0 feet, right? 0 miles. Oh, this one's easy then. This would be 264 rad per hour. Why did I draw an R? Who knows? Right?
Yeah, I will say it. I'll help you.
Classic related rates problem. 24-foot ladder is leaning against the house while the base is pulled away at a constant rate of 1 foot per second. We want to determine the rate at which the top of the ladder slides down the house. Right? So again, start by drawing a picture to visualize this. Okay, so what we have, right, is again a right triangle. We're going to say Y represents how high on the house the top of the ladder is. X represents the distance the base is away from the house. And we know that the length of the length of the ladder, rather, right, is 24 feet, and that's constant, right? We're going to assume that this ladder is not going to shrink or anything. It's not an extending ladder that you can shrink. If it is, it's locked in place, so it's going to stay at a constant 24 feet. All right, so we write out what we're given. Right? The ladder's being pulled away from the base. The constant 1 foot per second. Right, and then what do we want to find? We're going to find dy dt when x is located, or when the ladder is located some distance away from the house. The base of the ladder is some distance from the house. So we need a relation. Again, turn to our good friend Pythagoras. X squared plus y squared is 24 squared, which is just 576. Differentiate. Let's solve for what we want. But we know dx dt is 1. And so then y dot at x naught will be x naught, negative x naught rather, over y when x is x naught. We return to Pythagoras to determine that value of y is going to be the square root of 576 minus x naught squared. And of course, being measured in feet per second. Right? So now when the base is 1 foot away from the house, negative 1 over the square root of 575 feet per second. If you want to rationalize it, I know I can factor 25 from 575. No, that's not 23. It's 115. So negative root 23 over 115 feet per second, if you prefer it rationalized. And then just for perspective, it's about negative 0.04 feet per second. Right, 10 feet away. You should get the idea. We're just going to be plugging it in. Simplifying it, or you can pull a 4 out from the 476. If you prefer it rationalized. And just for perspective, about negative 0.46 feet per second. All right, we're now at 23 feet. So what is 23 squared? It is 529. Use it the square root of 47. And so about negative 3.35 feet per second. Now we're 24 feet away. Notice we're going to get negative 24 over 0. But think about this. If the base of the ladder is 24 feet away, doesn't that mean that the ladder is now lying on the ground? So we're no longer sliding down, right? We're already on the ground. So it has no velocity sliding down. Are there any questions? All right, moving along. Linear approximations or the linearization. The linearization is just the equation of the tangent line. Right? The idea behind this is for values really, really close to x naught, the function f can be approximated as its tangent line. What this does, this allows us to approximate some values. All right, so let's try and approximate the value of 2.05 squared. Well, let's use, obviously, x squared. Now we want a point, a value that is close to 2.05 that we know the square of in this case. Well, 2, wouldn't it? F prime is 2x. So we can find the linearization now. This allows us to approximate 2.05 squared as L of 2.05. Two point oh five squared is about 4.2. And compare this to what your calculator will give you. All right, so I think what I'm going to do is where is it? I updated it and never reattached it to my taskbar. That is too zoomed in. Let's try this. Yes. Gives us an error of 0.06%. Which means that's a really damn good approximation. Oh, perfect. I might just start doing this, not doing full screen, and just hide that. Avoid the massive problems I have. And what about 5.1 cubed? Right, well, we're going to be using the cubic function, right? And we can easily find 5 cubed. F prime of x is 3x squared. Our linearization then would be f of 5 plus f prime of 5 times x minus 5. Five point one cubed would then approximately be L of 5.1. All right, so 125 plus 75 times 5.1 minus 5, which is 125 plus 7.5 about. So assuming I did my basic arithmetic right, should get about 132.5. But again, if we compare, if we compare that to what a calculator would give us, .011% error. And so again, that's a really good approximation. What about square root of 24? Wow, I still have the same problems even. I don't go full screen, so what is going on? Square root of x. We need to pick an x naught close to 24 whose square root we know. The 25, right? F prime would be 1 over 2 root x. Might that be our linearization? Looks like square root of 24 is going to be about 4.9. If we compare that, let's see what kind of error we get. 0.02%. Do that real quick. I'm gonna try something else. Just as much of a pain, unfortunately, I think. What happens if I have this here and then I start, yeah, see? Windows 11 really messed things up. Cube root of 63, we're going to be using the cube root function, right? Let's actually write out f prime first this time. It's what? It's 1 over 3 cube root of x squared. So we need a value close to 63, whose cube root we know.
$64.
We get L of x, cube root of 64 is 4 plus 1 over 48. Times x minus 64. Okay, 63 is going to be about L of 63. It's going to be 4 minus 1/48. No way. There's gotta be. Should just approximate that as 0.2. The whole point of this is to not use a calculator, right? Yeah, so I'm just going to go ahead and say, oh, you know, these are approximations, right? So let's say 1/48 is about 0.02. And it's about 2 over 100. Which is what, 3.98 about? I don't know why I wrote that there. So let's say cube root of 63 is about 3.98. And so here we'll do two comparisons. So let's do the comparison with what we just did. So 3.98 cube root 63. So again, about 0.02% error. Yep, that's ugly. So, well, I can easily fix that with this. Just put a decimal point. Perfect. Increase the error by a factor of 10. But notice it's still a really good approximation. Although, to be fair, right, 4/148, that's a messy decimal to work with anyway. Right, let's look at sine of 3. Function we want to use is sine of x. Derivative is obviously then cosine. And we want a value close to 3 that we know the sign of.
Could you do pi?
That's a good value, isn't it? So we'll take pi. So linearization would be f of pi. So sine of pi is 0. That's nice. F prime of pi is 1. We just have x minus pi as our linearization. Sine of 3 is going to be about L of 3, which is just 3 minus pi. No, I'm sorry. Cosine of pi is not 1. It's -1. So this would be pi minus 3. If we take pi to be 3.14 as an approximation, then we're going to get what? That sine of 3 is about 0.14. And we get about 0.8% error. Right, so you're seeing that this is serving to be a pretty good approximation. All right, so let's do this. We'll take our break, come back at 7:50, and then continue on. And we're back. I think this is the last one for linearization. E to the 0.1. All right, obviously e to the x, right? Was our function? Now we need a convenient point. Why not 0? Linearization would be e to the 0, which is 1, plus e to the 0, which is 1, times x minus 0, which is just x. You get 1 plus x. All right. Then e to the 0.1 is going to approximately be L of 0.1, which is 1 plus 0.1. And say e to the 0.1 is about 1.1. Oh. So about 0.46%, 0.47% error. So if you're given a function y equals f of x, the differential for y is dy equals f prime of x dx. We just say dx is the change in x. Right. So what differentials allows us to do is they allow us to approximate how y will change, right? So approximate how an output changes at a point if we change the input. Right, so let's say we were given I don't know. Let's just go simple. Let's say we're given f of x equals log of x. And let's say we're at some point. All right. Okay. All right, so let's say we're at, I don't know, E.
Yeah, stop.
Well, we know that f of x is going to be 1. Well, now the question is, what happens if we increase the input? We increase E by 0.01. Well, the differential is going to allow us to approximate how that output changes. And by the way, differentials are also going to be important when we study integration. So what we're going to do is compute the differential for each function. So differential for y. We take f prime of x. And that's times dx. Well, it's a general power function. Right? So 2 times the function, and then times the derivative of the function. And then dx. And this is our differential. Excuse me for 1 minute. All right, what about here? Well, again, first we're going to want the derivative. This is a product rule. And then we just multiply by dx. Right. Derivative. This is a quotient rule. And then multiply by dx. And now this can actually be simplified. Can it? No. No, it cannot. That's a bummer. Derivative of the function. Well, we're dealing with a cosine function, right? So derivative cosine of u prime times negative sine of u. Then times dx. All right, derivative. This is a product. Right, then multiply by dx, and if we wanted to, we could also write it this way. I could write as a single fraction. And we could also write it this way. And it all just depends on how you like it. Derivative of a natural log, right? So derivative natural log of u is u prime over u. We get tangent x dx. Set of plastic spheres are to be made with a diameter of 1 centimeter. If the manufacturing process is accurate to 1 millimeter, what is the propagated error in volume of the spheres? All right, first off, what is the volume of a sphere?
Thirds pi radius cubed.
Okay. 4/3 pi r cubed. Let's find the differential for v. Right, 4 pi r squared dr. Well, we're told we have to be made with a diameter of 1 centimeter, so we know that the radius is 0.5 centimeter. What the? Ah, okay. I know. Okay, I see what I did. Perfect. Process is accurate to 1 millimeter. So dr would be half. I'm going to do it. It's actually plus or minus 0.5 millimeter. One of these got to be converted. Well, 0.5 centimeter is what, 5 millimeters? We can approximate the propagated error by dV. $25 times 4, right? 100 times pi times plus or minus 0.5. So the volume is going to have an error of plus or minus 50 cubic millimeters. No, 50 pi. Where did I just drop the pi? All right, if we want to write that back into centimeters, it's going to be what? 5 centimeters? Or no. It'd be divided by 1,000. Right, so it'd be 5 over 100. Plus or minus 0.05 cubic centimeters. Any questions on the linearization or differentials? Newton's method. So Newton's method gives us an iterative process for numerically finding the root of some function. And so remember, the root is solving f of x equals 0. We first have to make an initial guess. We call this initial guess x naught. The iterative procedure xi plus 1, or I'm going to use n, is x sub n minus f of x sub n divided by f prime of x sub n. And the idea is you keep calculating steps, right? So the iteration continues until you reach a desired accuracy. Now, here's the problem with all iterative techniques. You generally do not know how many steps you need until you actually do it. So what could wind up happening is maybe you only need 2 steps, right? You only need to go up to x2 to get your desired accuracy. Or you could need 200 steps or 2,000 steps. That is a massive pain to do by hand, right? Generally speaking, whenever we use a numerical technique, that means coding. For quiz and test purposes, I will either tell you the number of steps to use, or the accuracy is going to be chosen such that you don't need that many steps. The same cannot be said for homework. So what I'm going to do is I'm going to show you how we can do this on a calculator. And by writing up a simple code using Mathematica. Right? Or which is for us Wolfram Online, the Wolfram Cloud. That is Mathematica. Since this is all numerical, there's nothing for me to write down. So this is going to be pure technology. Okay, so first, I'll show you a calculator. Here we're only going out to 3 decimal places, which is nice. Okay, so again, I'm using the TI Nspire CX CAS.
Yeah.
All right. First thing we're going to want to do is look at a graph. All right, we have 2 zeros, 3 zeros. One here, one here, one here. We're going to look at the smallest zero first. This one here. Make an initial guess. -5. Right. Looks to be right around -5. So I'm going to take -5 as my initial guess here. All right. The first thing I want to do is define my function. I'm now going to define the derivative. Right, so what I can do is go up to menu, calculus, derivative. And I probably should have done and it needed to be a colon equals. There we go. Now I'm going to go first, document settings. I think I want fixed 3. No, I don't. Oh, let's just see what happens. Oops. I'm going to do -5. I'm going to hit enter. Actually, I'm going to do -5 decimal. Enter. Yes, I do want 3. Perfect. And here's why I did that. So remember that the iteration was xn minus f of xn divided by f prime of xn, right? So I'm going to go answer minus f of answer divided by df of answer, and then hit enter. So there's x1. Now, all I have to do is hit enter again, and it'll give me x2. There's x2. Now, look at x1 and x2. Do they agree to 3 decimal places? No, right? So we need to go again. So I just enter again. There's x3. Do they agree to 3 decimal places? They do, right? They're identical. So there's my first root. All right, so what I might do is so what I would do is on a test, right, I would just write out what my initial guess is. Then I would go, okay, x1 is x0 minus f of x0 divided by f prime of x0. Right, obviously have what f prime of x is, so I'd actually write out what the derivative is. And then I'd write down what we got, which was what, negative 5.167. Right, then I'd say x2, x1 minus f of x1 divided by f prime of x1. And then I'd write down what we got, which was negative what, negative 5 point, I think it was 156. And then I'd stop. There's my root. No, I might just write something like root equals negative 5.156, something like that. I don't know. Right, but that would be all the work I would need to see, right? Just write out the function, write out its derivative, and then just write these out. You don't have to actually write out every single value and do it all by hand. All right, now let's look at the middle root. And so again, we need to come back over, look at the graph. I don't know, negative 0.5. And then do the same thing. Answer minus f of answer divided by df of answer. And then there's x1. And so if I come over here, x0, we took to be negative 0.500, x1. And it was what? It was negative 0.381. All right, hit enter again. All right, negative 0.369. They do not agree to 3 decimal places. So go again. Negative 0.369. They agree. So then that's the root to 3 decimal places. Largest root, I don't know, let's go with, looks like 0.5 would be a good first guess. So 0.526, let's go with x2. We got 0.525. So we're going to need x3. All right, just hit enter again, and we get 0.525. They agree to 3 decimal places, so our root there would be 0.525. Right, so 2 problems with this technique. The one we already discussed. It's an iterative process, so it's a pain to do by hand. And you have no idea how many steps it's going to take you. The second problem is a bigger problem. This method is dependent on your first guess. Depending on your guess, your x naught, it could converge faster, right? So the number of steps you need could be less. It could converge slower, so you might need more steps. Maybe it doesn't even converge. So you're never going to get an answer. Or it converges to the wrong root. Right, so this is why it is imperative that if I do not give you an initial guess, which I am most likely going to do, you need to look at the graph and pick a value that is really close. Again, you don't have to be dead on as long as you're pretty darn close. So I would not, for instance, pick 0 for either of these 2 roots. Right? I don't know if 0 is going to go to this one or this one. If I had to take a guess, it would probably converge to this middle root here. because it looks like it's closer to that one than it is to the larger root. Okay. I still haven't done my account. Yeah, I don't care about Wolfram Desktop. I'll deal with that later if I really need to. I think 20% will be right. Okay. Help actually showed what the problem we're working on is. It's coordinate. All right, so we're going to look for the roots here. I don't want you. Let me first define my function. Shift enter. Now plot f of x. I don't know, let's go minus 10 to 10. All the way around. No. How did I do this before? Save as. No, I think it was over here, wasn't it? Let's download it as a JPEG. Just so we can zoom in. Right, 4 roots. 1, 2, 3, 4. Each tick represents 1. So let's start with the smallest root. And I'm going to do an initial guess of -4. So here's what I'm going to do. I'm going to define my x naught to be -4. I'm going to set my n to be 1. No, I'm going to set my n to be 0. I'm going to set my error to be 1. I'm going to use a while loop. I'm going to say while my error is greater than 10 to the -3, right? That's 3 decimal places. It's going to calculate the next step. So I want it to calculate xn plus 1. That is xn minus f of xn divided by f prime of xn. All right, semicolon. So this is the body. I can just do the print now, I think. I'll have it print before I do anything else. So I'll have it print out. Anything in quotation marks is text. I want 4 digits here. Right? So I'm telling it to print, this is the text. It'll print out whatever the n plus 1 value is. More text. This gives it a numerical approximation of what was just calculated, the xn plus 1, keeping it to 4 places, 4 digits. At least I hope that's what it's going to do. Then I'm going to have it set the error to now be the absolute value of xn plus 1 minus xn. And then I want it to set n to be n plus 1. Right, so n plus plus essentially. Which you can also just write that, I believe. You can just do n plus plus and it'll add 1 to n. Right, so what it'll do then is it adds 1 to n. Now it's the end of the body, so it's going to check the test again. If the test fails, it stops. If the test doesn't fail, it'll repeat this process. So if I now execute it, all right, there it is. So the problem is it takes each of these as a different bloody cell. I don't think oh, it will let me select multiples, but yeah, it's only going to do one of them at a time. That is really annoying. I guess I could just do this. No, actually what I want to do is take the whole thing. Yeah, that'll work. All right, so this here would actually count as my work. So on a test or a quiz, you are free to do this. Right? Just make sure that you include the code. So you include this bit here, this entire bit, in with your answer. All right, so the easiest way to do that would be just to print it out and like tape it on to the work before you scan as a PDF and upload it. And if you don't have a printer, Word doc, you can just post a picture of your work and then a picture of this beneath it, and then save that Word doc as a PDF and upload it. Right, but now here's the beautiful thing about how I wrote it, right? And that's the reason I wrote it this way. And the middle small root. So look at that. Looks like -1 would be a good guess. I probably don't even need to write that out, but whatever, I will. All I have to do now is change that to -1. And then re-execute this. Right now, in this case, I actually didn't need 4 digits here. Right, so if I wanted to, I could now go back and just change this to 3 and re-execute. All right, then I'm just gonna screenshot it, attach it, and let's just shrink it so I can get it on screen. And the root would be -0.857.
Yeah, I'm gonna send it to her.
I'm going to use +1 for this third root, the middle large. All right, come back here. I'm going to make that 1 just to be safe. I'm going to switch this back to 4 digits, execute. And it was exactly 1. Look at that. on 1.5 for the large root. All right, let's change that to 1.5. Everything else stays the same. Let's execute it. And now I don't know why it's not. Oh, yes, I do. I know why. So instead of 1.5, let me write that as 3 over 2. So I can get the 3 decimal places. Although it didn't. These do not agree to 3 decimal places. What if I change this to greater than or equal to? Doesn't change it. So why is it? Oh, is it because of rounding? It is. Okay. It's because of rounding. So that's fine. All right, so that's 2 methods, calculator and the Wolfram language for Newton's method. Are there any questions on either of those 2 methods before I look at some more problems? All right, so I'm going to find the roots of the 17th degree polynomial on the open interval -2 to 2. All right, so I'm just going to make a few adjustments. To here, right? Also, I'm going to redefine my f. What's going on? There we go. So re-execute that. The plot, I'm only going to go -2 to 2. Now let's download that. It's a JPEG again. Zoom in. All right, so there's 3 roots on this interval. I'm going to take -1 as my first guess. And just take that as my work. Actually, let's just do it this way. This method better. All right, what do we think? Guess for the second. 1, looks like, right? I'm going to change this to 3 just so I can keep the 3 decimal places. And then copy that as my work. Good enough. And for the third, so it looks like 1.4. Could be 14/10. Don't care, that's not simplified. And there we go. Right. So it also lets us do some really ugly ones, right? Like this. And so restore that. They want -3 to 3. So let's flop that. Download this as a JPEG. Zoom in. It looks like we're gonna have 4 roots. All right, you get the general gist. So I'll let you do this one on your own. Because there's one other application I want to show for Newton's method. So let's say I want to get an approximate value of square root of 2. And let's go 6 decimal places. Well, square root of 2 isn't that a solution of x squared minus 2 equals 0? And we can use Newton's method. Now, I happen to already know close enough what the decimal approximation of root 2 is. I'm going to do an initial guess of 3/2, 1.5. The only thing I have to change here now is I want an accuracy of, let's say, 6, right? I want to go 6 decimal places for root 2. And obviously, you should have been 7. Uh-oh, why is it now taking... did I never... Uh-oh. Oops. Abort. Yep. I never actually stored this. There we go. Apparently I did. No, it's not. What's going on? Abort. Oh dear, did I just break something? Something just broke. Okay, there we go. I just want to make sure this did go in okay. It did. Now let's try this again. Now it should. There we go. So the 6 decimal places, square root of 2 is 1.414214. What if I want more? Let's go out to 10 decimal places. All right, there you go. So as long as the number you're trying to approximate is the solution, is the root of some function, You can use Newton's method to approximate it within a certain accuracy. All right. So we can also do pi, can't we? Ten digits of pi, 3.14159265636. Or 10 decimal places, so that's 11 digits of pi. See that? Any questions on Newton's method? Okay. Finishes those. Right? So you have the next reflection, unit 2 reflection. Let me check. That is due, looks like tomorrow night. It is, it's due tomorrow night. The first post for the derivative discussion is also due tomorrow night. But you have 3 assignments on My Up Math. Those won't be due until August 4th. And then you have the 6th quiz, which will be due before class starts tomorrow. If you take a look at what we're doing tomorrow, just 2 things on the docket. So tomorrow might be a fairly short night. We're looking at L'Hopital's rule, which is a great tool for evaluating limits of certain indeterminate forms. And then we're also looking at extrema. More specifically, our focus is going to be on finding absolute extrema on closed intervals. And so that is the goal for tomorrow night. All right, thank you for your attention. Everyone have a wonderful rest of your night. I will see you again tomorrow evening, 6 p.m.
Thank you.
Thank you.